In the last video, we analyzed a resistor inductor circuit, and we got a first order differential equation that describes the current in that circuit. So I can rearrange this equation a little bit. I can basically kind of algebraically solve for the current, and I will get the following. So just bringing the derivative to the other side and all of the constants together, this is what I'll get. So I want to try and solve for the function I in this equation. And there's a few strategies that you can follow, but the first one I want to show you is a method called substitution. So the way that this works is I think about what this equation actually represents. And so thinking about this here, basically what this is saying is we need a function that is equal to its own derivative times a constant. Right, we're saying here in this equation that our function I is equal to some numbers multiplied by the derivative of that function. So something that is proportional to its own derivative, and there's only one function in mathematics for which that is true. And you should kind of hear the voice of your math teacher kind of ding, 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 like you should have this idea in your head. You should know this. The only function for which this is true is the exponential. So you're thinking here, the only function for which this is true is the exponential. Right? Think to yourself, you have polynomials, you take the derivative, it's no longer proportional, right? The power changes. Trig functions, sine changes to cos and so on. So the only thing where it stays the same, the shape of the function stays the same, but you get some constants out the front, that's the exponential. So we can use this thinking and take a fairly informed guess. So therefore, I of t must be of the form I of t is equal to some constant, let's call it a, times an exponential of some other constant, let's call it b, times t. It's the only way for this equation to be satisfied. So you think to yourself, well, here this function is proportional to its own derivative, and so let's assume we have an I of t of this form and substitute it into our equation. Okay, so now substitute I of t into the differential equation. All right, in order to do that, I need to know the time derivative, so I need to know di dt, which in this case is just going to be a b e to the bt. So the b coefficient just comes down the front when I take that derivative. Okay, so our equation was, let's remind ourselves, I of t is negative L over R times di dt. All right, let's sub in what we are assuming. So we're assuming that a e to the bt is equal to negative L over R times a b e to the bt. And this is kind of nice because we can see that this equation will be true for certain values of b. So we're going to be able to solve for some values of b here. So let's actually simplify this equation. So I can cancel a on both sides. I can cancel e to the bt on both sides. So an exponential is never equal to 0, so I can divide through by it, so that's all legitimate. And what I'm going to end up with is just 1 is equal to negative L over R times B. In other words, B is equal to negative R over L. Just bringing that one to the other side. So that's good. We're making some progress. So therefore, what we have now for our current I of t, that one is equal to coefficient A, which we don't know anything about just yet, times e to the negative R over L, so that was our coefficient, times t. That's a little bit messy, so I'm going to write it as this exponential. So it's negative R over L times t, like that. Okay, so how do we find the coefficient here, A? And so for that we need to know the initial condition. So to find the coefficient A, we need the initial condition. So every differential equation requires initial conditions. First order differential equations require a single initial condition. So this is a first order DE, so we need one initial condition. And so that will usually be in the form of what is the current at a particular time. So e.g. The current, so I of t at a certain time. Now in the last video when we analyzed the circuit, what we concluded was that we knew the value of the current at t equals 0. And that was some constant I naught that came from the power supply in our circuit. So what we can do is substitute this information into our expression here for the current. So we substitute t equals 0 and I of naught equal to our initial condition, and here's what we'll get. So I naught on the left hand side, substituting t equals 0 into here will give us I of naught, and I of naught is just our value that we got from our power supply. So we have that is equal to A times the exponential of negative R over L times 0. An exponential of 0 is equal to 1. All right, so all this bit here is just equal to 1. So therefore what we have is I naught equals A. So therefore our final solution is I of t is equal to our initial value I naught, that's subbing in for our coefficient A, times our exponential, which was negative R over L times time t. And this equation satisfies our differential equation. So you could take this solution, and you could substitute it back into our differential equation. You could sub it back into here and simplify, and you will end up with just I of naught. So that's how you can kind of check your working. So this is one way that you can approach solving differential equations, and the only thing that it really requires is this leap of faith where you recognize, because you have a first order differential equation, the solution is always going to be an exponential. That's true for every first order DE with constant coefficients. So if the coefficients are constant, if it's a linear differential equation, linear meaning that there's no like I squareds or squared terms involving the derivative, things like that. If it's linear and it has constant coefficients, the solution will be an exponential. So you can assume that you know the correct functional form, just you don't know the coefficients, and then you substitute into the equation, do some math, and find out the values of those coefficients, and that leads you to the final solution.